we start off very fast in this class. And there's no time that I'm giving you where you can't have a lesson mastered. This is very true off the get-go. I have 1 day to review the unit circle. You guys have to have the unit circle mastered on Monday, because after Monday, trigonometry will show up randomly in this class. And I can't tell you, oh, hey, be ready for some trig stuff on the next quiz. You might have a homework assignment that has no trigonometry, and then on the following quiz, it has a question involving calculus that has trigonometry in it. So, before Monday, if you guys don't feel comfortable with the stuff that I'm doing here, you need to work a lot. You need to come in and see me. I'll give you extra practice problems. You need to do the homework over and over again until you're getting every single problem right every single time. There's no room for you guys to slowly work into things if you are uncomfortable with any of this stuff. Does that make sense? Okay, good. Okay, with that being said, this is how I do a problem like, what is the sine of 2 pi over 3? Okay, if somebody asks me, what's the sine of 2 pi over 3? I'm going to tell you what I think about when I do it. You might do something else. Maybe you learned it a little bit differently. That's okay. You can do it that way. However, what you're not going to be able to do is use a manipulative. So any sort of reference sheet, can't use that. And the way that you have needs to be able to be accessed quickly and then forgotten about. So if you like write down the entire first quadrant of the unit circle or something like that, that's not going to fly here. You got to be able to say, oh, I know what that is because I'm thinking of this and this, and boom, there's the answer. Okay? I'm going to show you how I get the sine of 2 pi over 3. Okay? Here we go. First thing I remember is my friend, the acronym SOHCAHTOA, which tells us that the sine of an angle is equal to the ratio, and this is an angle in a right triangle, is equal to the ratio of the opposite side divided by the hypotenuse. The cosine, or the cosine of an angle in a right triangle is equal to the ratio of the adjacent side divided by the hypotenuse with respect to that angle, so the adjacent side to the angle. TOA, tangent, is equal to the ratio of the opposite side to that angle in a right triangle divided by the adjacent side. So I got to remember that. I also need to remember the reciprocal functions. So the reciprocal of sine is cosecant. Cosecant would be hypotenuse over opposite. Reciprocal of cosine is secant. Secant is hypotenuse over adjacent. Reciprocal of tangent, cotangent. Okay, that's the first thing I need to know. Second thing I need to know are the side lengths of a 30, 60, 90 and a 45, 45, 90 triangle with a hypotenuse 1. So all of these right triangles have a hypotenuse of 1. Might not look like they're the same length, but let's just pretend. These are two of the same triangles, just oriented differently, okay? This is what I consider the tall 30, 60, 90 triangle. This is what I consider the short 30, 60, 90 triangle. Now, the bigger angle is opposite the bigger side length, vice versa. So, same angles, 30, 60, 90. Now, we can use trigonometry to show that for a 30, 60, 90 triangle, the shorter side length is 1/2. The longer side length is √3/2. I know √3/2 is bigger than 1/2 because I know √3 is bigger than 1. And since root 3 is bigger than 1, root 3 over 2 is larger than 1/2. So I consider this the longer side. Now the longer, like, shorter. Okay? Vice versa. For our 45, 45, 90 triangle, we can use the Pythagorean theorem to quickly show that these side lengths are root 2 over 2. Okay? So that's the first couple things I'm going to remember and I'm going to use. Next thing I'm going to use are radians. So in this class, we do not use degrees whatsoever. Sometimes it helps to kind of refer to degrees, but we will not be using degrees at all. We will be using radians all year. Whenever we use our calculators better be in radian mode. Okay? And a radian, it's important to understand what it is. It is a distance around a unit circle. Here is my unit circle. We call it a unit circle because its radius is 1 unit. So from the origin here, 0, 0, to the outside of my circle, or to my circle, we have a distance of 1 all the way around. Okay? Now, if radians are distances around the unit circle, we have talked about distances around circles before. There is a term that we used in past math classes that talk about a distance or a perimeter around a circle. Discuss with your neighbors. Go ahead and feel comfortable with each other. It's a short class, so we can ask. Discuss with your neighbors. What is that term that we've used in the past that talks about a perimeter of a circle? Circumference is the right answer. So the circumference is the term that we've used in the past for distance around a circle. Okay? Now, who remembers the formula for the circumference of a circle? 2 pi r. A lot of people think pi r squared, but what's that?
That's the area.
That's the area. Good. So, distance around a circle is 2 times pi times r. Distance around a unit circle is just 2 pi. So around this unit circle, there's a distance of what we say 2 pi radians. But, where do we start? Okay, like where's the starting point where I say, okay, start here, go around the circle, 2 pi. Because if I start here and go around the circle, yeah, that's a distance of 2 pi. But we need a starting point. So this is what I'd like to have you kind of envision, is that you're a person standing with your head at the origin. And you are looking off into the distance. So I'm standing right here looking that way at the horizon. We'll call that 0. That's our starting point. So here, we'll call that 0. That's my starting point. This is me looking into the horizon. Now I can either look up or I can look down. But I'm kind of adding to my angle created, which is adding to the distance. Well, if I look up, we'll call that adding to an angle. So if I look up and then I continue to go all the way around my circle, we'll go this way. And that is what we'll consider going in a positive direction, or counterclockwise, we'll be adding. If I look down, we'll call that like a negative angle, or if I'm going clockwise, I'm going in a negative direction, or I'm subtracting. So what I would be doing is going from 0, traveling around this circle, this distance. I get all the way around the circle. We call that 2 pi radians. So around an entire circle, it is what you guys have known to be 360 degrees, is the same as 2 pi radians. Okay, great. Now, what if I wanted to just go halfway around the circle? So we know that as being 180 degrees. Well, what's halfway between 0 and 2 pi? Pi. Well, pi is 180 degrees. Now again, if I got to pi and I wanted to add angles, again, it's kind of tough. I'm not going to think about it as going up or down. Instead, we think about this way is adding. So I'm actually going counterclockwise, and this way would be considered adding more angles or more distance, and this way would be subtracting. So keep that in mind. But that's pi, that's 180 degrees. Now what's halfway between 0 and pi? Pi over 2 divided by 2. So pi over 2 right here would be what you guys have thought about as 90 degrees. So starting at 0, looking at the horizon and looking straight up, 90 degrees, that's pi over 2. Okay, great. We could go the same thing about going to pi and then adding another 90 degrees. Well, if this is 90 degrees, pi over 2, I can go further and add 90 degrees, add a pi over 2 to pi, and I get to 3 pi over 2. We could do that, but we'll do that another way. Okay? Well, what I've done here with these lines is I split this into thirds. It's kind of exaggerated thirds. But let's say I take 90 degrees and I divide it by 3. What do I get? 30 degrees. Okay, well, if I do that, that's the same as taking pi over 2 and dividing it by 3. Dividing it by 3 is the same as multiplying it by 1/3. Pi over 6. So pi over 6 is the same as 30 degrees. So if this is thirds, start at 0, add 30 degrees. That's going a distance of pi over 6 radians. All right, so don't have to have this, but we do have to know that pi over 6 is what you guys think of as 30 degrees. Now, if I add 30 degrees to 30 degrees, so I start at 30 degrees and I add 30 more degrees, I get to 60 degrees, right? Well, you can do the same thing with radians. I can start at 0, add a pi over 6, and add another pi over 6. Pi over 6 plus pi over 6, 2 pi over 6. Well, 2 pi over 6 is the same as pi over 3. If you just simplify the 2 over the 6. Well, that is created a 60-degree angle. It is important to remember that the pi over 3 is 60 degrees. But let's keep going. Let's see if I see any different type of angles. So I get to pi over 6, 2 pi over 6, 3 pi over 6 is pi over 2. That's good. We already have that. That's 90 degrees. Add another 30. I get to 120 degrees, 90 plus 30. So 3 pi over 6, this would be 4 pi over 6. Okay, well, 4 pi over 6 simplifies to be 2 pi over 3. Now, 180 and 120, that means that this angle is 60 degrees away from the x-axis. This is very important, what we call this reference angle to the x-axis. If I add another pi over 6, I'll get to 5 pi over 6. This is 4 pi over 6, 5 pi over 6. Well, let's see, I got 90, 120, 150. So 150, that's only 30 degrees away from 180. So this is just 30 degrees, and this is important to know that that's just 30 degrees away. I get to pi, that's 6 pi over 6, 180 degrees. Add another pi over 6. 6 pi over 6 plus pi over 6, 7 pi over 6. Keep adding, 8 pi over 6. 9 pi over 6 can simplify to be 3 pi over 2. 10 pi over 6, 10 over 6 simplifies to be 5 over 3. 11 over 6 does not simplify. But going through this, 30 degrees at a time, or a pi over 6 at a time, I noticed something very interesting. Every single pi over 6 angle measurement creates a 30-degree angle with the x-axis. So it's not just pi over 6 creates kind of a 30-degree angle. I'm going to say any pi over 6 creates a 30-degree angle. It's not just these two pi over 3s. All of my pi over 3s create a 60-degree angle with my x-axis. So any pi over 3 gives me a 60-degree angle. Okay? One other we did not talk about is if I took this 90 degrees here from 0 to pi over 2 and I split it in half. What's 90 divided by 2?
45.
45. What's pi over 2 divided by 2?
45.
It's 45 degrees, but in terms of an angle. Pi over 4. Beautiful. So this angle right here, which creates a 45-degree reference with the x-axis, is pi over 4. And I actually can go around the entire circle just by adding 45 degrees at a time. So I get 45 to 90 to 135, 135. So this is 1 pi over 4, 2 pi over 4, 3 pi over 4 creates a 45-degree angle with the x-axis. 4 pi over 4, 5 pi over 4. 45 degrees again. 6 pi over 4, 7 pi over 4. 45 degrees again. All of my pi over 4s create 45-degree angles with the x-axis. Okay? Great. Now, why is that important, understanding these angles relative to the x-axis? Because of something we'll get to shortly. But before we get there, it's important for us to not have to do that to find every single angle measurement. Not have to recreate the unit circle in radians and think about, okay, around an entire circle, 2 pi radians, halfway around would be half, that gives me pi, half that's pi over 2, divided by 3, that's how I get pi over 6, and it's 30 degrees. It's important to be able to do that quickly. Like if I ask you, where is 2 pi over 3? Or where is 7 pi over 6? How can you get there quickly? And let me tell you how I do it. Okay? Well, I know this angle over here, pi, can be written a lot of different ways. It could be written as 6 pi over 6. Let me move it over. It can be written as 3 pi over 3. It could be written as 4 pi over 4. Right? Those are all just versions of 1, 3 over 3, 4 over 4, 4 over 4, 6 over 6. Well, 7 pi over 6 is just 1 pi over 6 added to 6 pi over 6. Or 1 pi over 6 added to pi. Well, since I know when I go counterclockwise, I'm adding. If I start at 6 pi over 6 and I add a pi over 6, knowing that the pi over 6 is 30 degrees, I know that I'm going to be located right here in the third quadrant, creating a 30-degree angle. And this, my friends, is how I will quickly locate 7 pi over 6. If I ask you to locate 2 pi over 3, this is what I would do. I would start by saying, hey, I know where 3 pi over 3 is. Probably should have done this in an opposite order, but whatever. If I subtract a pi over 3 from 3 pi over 3, I get to 2 pi over 3. Well, again, remember when we look into the horizon, going up would be adding, so counterclockwise. Going clockwise would be subtracting, so going clockwise would be subtracting. Here's 3 pi over 3 right here. If I subtract a pi over 3, I'd be going this way. Knowing that a pi over 3 is 60 degrees, that's why I'm going to be located here, where I have a 60-degree angle created. Okay, tricky ones that people have difficulty with are 5 pi over 3 and 4 pi over 3. Here's what I would do. I'd actually not go to pi. I'm actually going to go all the way around my circle to 2 pi, which is 6 pi over 3. I can write 2 pi a lot of different ways. That's 6 pi over 3. That's 12 pi over 6s. That's 8 pi over 4s. Knowing that when I subtract, I go clockwise, I could start at 6 pi over 3s, subtract a pi over 3, and boom. I create a 60-degree reference angle again. And here is 5 pi over 3. Okay, why don't you guys try, find for me 5 pi over 4. Find pi over 6. Find 5 pi over 6. Okay. Ready, set, go. Find those 3 angles. Don't look back. Do it without looking.
Oh.
That's your key. There you go. Good. So now we got to get the 5 pi over 4.
Yeah.
This is also 4 pi over 4.
Okay, so yeah, yeah.
Which way is adding, which way is subtracting? Okay, good. What's that?
I'm thinking it would be 3 pi over 4?
Yep.
Yeah.
Did you just recall that from memory, or did you figure it out?
I figured it out.
All right, good. Because that's what we got to do.
You see I'm drawing out the thing.
Yeah, but this is what I don't want you to do. Because we have to be able to Not do it from memory. I don't want you to do it from memory, but rather like be able to recall the thought process that gets you there rather than the overall creation. Like what we did here, I don't want you to be able to do this. You don't have time to do this. Okay. You need to be able to say 5 pi over 4. Oh, here's 4 pi over 4. Add a pi over 4. I'm here. Pi over 6. Well, it's just 30 degrees. It's right there. That's an easy one. 5 pi over 6. I know where 6 pi over 6 is. Subtracting would be this way. Adding would be this way. I'm subtracting a pi over 6. I'm placed here. 30 degrees here. 45 degrees here. 30 degrees there. Okay? Questions? Okay. That and this is important because what we're going to do is we're going to be able to locate these angles like 5 pi over 6. But watch what I can do if I just take the location on my circle and I drop down vertically or put up vertically a line. I create one of the triangles that we talked about, these 30, 60, 90 or the 45, 45, 90 triangles. Because I remember a pi over 6 gives me a 30-degree angle. So this is 30 degrees. Since I know this is 30 degrees, I know I've created what I consider my short 30, 60, 90 triangle. Which means the short side, the 1/2, is the vertical side. The long side, root 3 over 2, is the horizontal side. Don't worry, I'm going to come back and change that. But for right now, I'm going to leave it like that. Let's say this is pi over 4. I remember that a number pi over 4 creates a 45-degree angle with the x-axis. If I drop down a line, I create one of the special 45, 45, 90 triangles. I'm not even going to worry about the other angle. This has side lengths of root 2 over 2 and root 2 over 2. If I'm down here, I can start at my unit circle and go up to the x-axis. Let's say this is 5 pi over 3. Well, remembering that pi over 3s create 60-degree angles with the x-axis, I know that I have my tall 30, 60, 90 triangle. The two side lengths I have to choose from are 1/2 and root 3 over 2. I remember that root 3 over 2 is bigger than 1/2. So root 3 over 2 is my longer side. 1/2 is my shorter side. So this is important. Understanding that we can place right triangles in this circle, key. Combining that with this fact is going to put it all together. When I write my triangles, draw my triangles, and understand my angles created with the x-axis. Turns out, though, there is some kind of necessary math involved to show you why it is, but we're just going to not worry about it. If this is the unit circle, all of these triangles have a hypotenuse of 1, right? The sine of all of these angles, and these are the angles that we are going to worry about, these reference angles with the x-axis, always equal to opposite over hypotenuse, right? Well, the hypotenuse is always 1. Okay, so that's Good. I don't have to worry about the hypotenuse because dividing by 1 doesn't change anything. The opposite side length is always the vertical distance of my triangle that I create, or the vertical distance getting to the points that my angle is producing. That's key. If I look at the cosine, for all of these angles, cosine is adjacent over hypotenuse, right? But again, hypotenuse is always 1, and the adjacent side length is always this horizontal distance. This horizontal distance. This horizontal distance. Cosine is always the horizontal distance of your triangle that you've created. Tangent? Always opposite over adjacent? Well, it's always the vertical divided by the horizontal. So it turns out like the H, I don't have to worry about it. When I draw my triangles, I don't even have to write it down. Just have to care about the vertical side lengths and the horizontal side lengths. All right. This are the things that I understand, and this is how I know what the sine of 2 pi over 3 is. It's not through memory, it's through triangles and angle locations. Ready? Here's what I do. I'm going to do it verbally and then I'll write it down. I start with locating where 2 pi over 3 is, okay? So I'm thinking, here's 0, 2 pi over 3. Okay, I know what 3 pi over 3 is. Subtract a pi over 3. It's a pi over 3, so there's a 60-degree reference angle. In my head, I am creating my 30, 60, 90 triangle, but it's the taller triangle because of the 60-degree pi over 3 angle. So I'm thinking taller triangle, sine deals with opposites or vertical distances, always on the unit circle. So my vertical distance of my tall 30, 60, 90 triangle is a longer distance. It's the root 3 over 2. That is how I know that this is root 3 over 2. Okay? Now, I forgot to tell you one thing. Go back here. We talked about how you like add angles and it's going like counterclockwise is positive and then clockwise is negative. There are other positives and negatives that we have to worry about. And that has to deal with the origin and the x-axis and the y-axis. We know that this is like 0, 0 if we think of this as an x-axis and this as a y-axis. The other positives and negatives we have to worry about is traveling from the origin. I'm going to say this measurement right here is actually negative. I'm going to say this measurement right there is negative. However, 1/2 can stay positive. This root 3 over 2 can stay, this root 2 over 2 can stay positive. This root 2 over 2 can stay positive. This 1/2 can stay positive. Why I make these negatives is because if you're traveling to the left from the origin, you're going in a negative direction. If you're traveling down from the origin, you're going in a negative direction. To the right, positive, up, positive. Okay? So we got kind of two sets of positives and negatives to think about, like adding and subtracting angles, but then like traveling from the origin on the XY axis. Positive to the right, negative to the left. Think about coordinates. Negative coordinates. Okay? Forgot to mention that, but didn't matter for the sine of 2 pi over 3. But it will matter for the cosine of 7 pi over 6. And again, this is what I'm doing in my head. I'm creating the angle measurement. Here's 3 pi over 3. Subtract a pi over 3. Subtracting is going that way, right? Subtracting is going clockwise. Here is 2 pi over 3. I then create the triangle in my head. I understand it creates a 60-degree angle, which means I have a longer side, which is the vertical side, and a shorter side. The shorter side, since I'm going to the left, is negative, but since sine deals with just the vertical side, this is why I'm picking root 3 over 2. That's what I do in my head. Cosine of 7 pi over 6. Ready? In my head, this is my thought process. Find 7 pi over 6. All right, well, this is 6 pi over 6. Add a pi over 6. Okay, this is subtracting. This is adding. Counterclockwise, clockwise. 7 pi over 6 is 1 pi over 6 more than 6 pi over 6. Putting me right here in the fourth quadrant, but creating a 30-degree angle because it's a pi over 6. Creating my shorter 30, 60, 90 triangles, which means the vertical side length is the shorter side length. It's the half. The horizontal side length is the longer side length. It's the root 3 over 2. The half is negative. The root 3 over 2 is negative because I go to the left and down from the origin to get to this point on my unit circle. I'm not drawing the circle anymore, but we're pretending like this is the point on my unit circle. I go to the left, I go down. Cosine deals with horizontal, the horizontal negative root 3 over 2. Tell me first, what is the cosine of 5 pi over 3? Ready, set, go. Figure it out. I changed it from secant to cosine, and then we'll change it back to secant.
What did you say?
I changed this problem from the secant of 5 pi over 3 to cosine 5 pi over 3. But we will also figure out the secant of 5 pi over 3 at the same time. You need to try to do it without using any references. If you can't, you'll need to work on it between now and Monday, because this stuff has to be mastered between now and Monday, or else it will haunt you for the rest of this class. You're going to the right. Good. Six pi over 3. 2 pi. 6 pi by 3 is 2. You're thinking about 6 minus 2. So only pi over 4s create those 45, 45, 90s.
Okay.
The pi over 3s and the pi over 6s create the 30, 60, 90s. So this is a 30, 60, 90. You just have to figure out the orientation of it. Is it the tall or the short? You won't be able to use that. Good, good, good. Okay, now, this is what you need to do. You need to locate 5 pi over 3. It is 1 pi over 3 less than 6 pi over 3. 6 pi over 3 is here at 2 pi. Subtract that way a pi over 3. Pi over 3, the taller 30, 60, 90 triangle. Taller 30, 60, 90 triangle has a longer vertical side and a shorter horizontal side. The vertical side would be negative because you're going down. The horizontal side would be positive. This is why this is 1/2. If I asked you what the secant of 5 pi over 3 is, you'd say it's the reciprocal, 2. Or you'd say secant of 5 pi over 3 is equal to 1 over the cosine of 5 pi over 3, which is 1 over 2, which is 1 times 2 over 1, which is 2. Okay? So here's my answer to the problem. All right, before we do cosecant of 5 pi over 6, find the sine of 5 pi over 6. Locate the angle measurement. Create the triangle. Understand the longer, shorter sides, the horizontal, the vertical side lengths. Okay. 6 pi over 6 minus subtracting
Otherwise.
adding. Okay, if you always have to come back to here and think about looking out into the horizon and thinking, okay, adding angles, looking up into the sky, looking down into the ground, subtracting angles. So if you start there and then say, oh, okay, so that's adding. Okay, looking down into the ground. Okay, that's subtracting. Okay. Well, why do I not care about the hypotenuse?
I do care about the hypotenuse.
I don't care about it. Yeah, because it's 1.
I was asking what how to figure. It's been 3 months
Well,
longer, so
that's why this one.
opposite. I was just trying to remember.
Opposite what? What do you mean?
Opposite over hypotenuse. What I'm asking you is how would I find the opposite?
So
Which one?
we are always talking about the angle that is created with the x-axis. That angle.
Okay, so the opposite is always going to be the one that touches the x-axis.
The opposite is always the vertical distance in the unit circle, like we said. We should rewatch videos, okay?
What did you say?
We should rewatch videos. So that stuff that we missed the first time around, we'll catch the second time, okay? 5 pi over 6 is here. It creates a 30-degree angle, which is a shorter 30, 60, 90 triangle. It's got a positive vertical length, but a negative horizontal length. The vertical length is shorter because it's the short 30, 60, 90 triangle. Sine is opposite. We are always talking about this angle. Opposite is always the vertical side distance. This is why this is 1/2. This is why this is 2. Okay. Tangent of 11 pi over 6. Tangent, TOA, opposite over adjacent, but it's vertical over horizontal. You just need to be able to find 11 pi over 6. You need to be able to create the triangle. You need to understand the orientation, if you're going to the right or down or left or up. So that'll tell me if the lengths are positive or negative. Root 3 over 2 is the longer side length. Yep, root 3 over 2. Okay, but I'm going down Since I'm going down.
So you said the opposite is always the vertical side.
Yep.
All right.
Since I'm going down, that is what? So on a y-axis, there you go. Very good. Okay, you fixed it there. Good.
Yeah.
Good.
I don't do it.
Now this ended up being root 3 over 3, 6 divided by 2.
Oh, yeah.
Okay. I first find 11 pi over 6. 1 pi over 6 away from 12 pi over 6. Here's 12 pi over 6 right here. It's the same as 2 pi. Subtract, looking down into the ground, ends up being clockwise. So that puts me here, 11 pi over 6. 11 pi over 6 creates my shorter 30, 60, 90 triangle. In my shorter 30, 60, 90 triangle, the vertical side is the shorter side, but it's negative because I'm going down. The horizontal side is the longer side. It is positive. I'm going to the right. Tangent, opposite over adjacent, in the unit circle, with my reference angle always being there next to the x-axis. Opposite is always vertical. Adjacent is always horizontal. So, vertical divided by horizontal. Now let's simplify this a little bit. Fractions, the same as multiplying by reciprocals of the one that we're dividing by. This simplifies to be negative 1 over root 3. That is acceptable in this class for a free response question. You do not have to rationalize for free response. However, you may have to rationalize for a multiple choice question where you do not see this answer. I don't think that this is incorrect in any way. This is the correct answer. Okay, and in the calculus class, you'll see test questions where they'll have square roots in the denominator. They do not rationalize everything. You need to be prepared, though, to rationalize. Multiply the top and bottom by the square root in the bottom. You end up with negative root 3 over 3. Okay? Do the sign of 5 pi over 4 if you haven't done so already. Check your answer with a neighbor, please. Four pi over 4 is the same as pi. Add a pi over 4. Adding would be going in a counterclockwise direction. Here's 5 pi over 4. All the pi over 4s create those 45, 45, 90 triangles. So we know the side lengths are root 2 over 2 and root 2 over 2. Sine, vertical. Since it's vertical, and since I'm going down, the answer is negative root 2 over 2. Okay? Do a little bit more. We'll take a little break. Knowing that cosine of an angle always is adjacent over hypotenuse, but it always gives, it's always going to be the horizontal distance, and sine is always going to be the vertical distance. Tangent's always going to be the vertical divided by the horizontal. I know quickly and easily, without having memorized anything, that the cosine of 0 is not 0. It's 1. And here is how I know that. If I travel to the unit circle location of 0, so let's just draw a unit circle really quickly. I'll do the best that I can, and hopefully it'll pop. There we go. I got it. Okay. Traveling to this location on my unit circle at 0 from the origin, I go to the right 1 unit. I do not go up or down at all. Distance is 1. That's why the cosine of 0 is 1. However, if I ask you what's the cosine of pi over 2? Well, thinking about it the same way, if I go to this location of pi over 2 on the unit circle from the origin, I do not go left or right at all, but I do go up. Genius hours and stuff. I'm not sure. This is why the cosine of pi over 2 is 0, because I do not go to the left or right. However, the sine of pi over 2 is 1. You guys discuss with your neighbors what the answers to sine of 0, cosine pi, and sine of 3 pi over 2 are, and why they are what they are. Nope. Think about it. How do you get to pi? How do you get to pi from here? What direction do I travel?
Clockwise?
No, from here. Left. Answer, that's the answer. Left. You go left. How much do you go left?
1.
You go to the left 1, we'll call that a distance of -1, right? Why is it 1? It's a unit circle. I go left 1, it's a distance of -1 because I'm going to the left. So what's the cosine of pi?
0.
No.
1, -1.
We say them all, we'll figure it out, right? Since cosine is the horizontal distance, since I'm traveling a horizontal distance of -1, the cosine of pi is -1. That's why. I don't have this memorized. I think about it. What's the sine of 0? Why? I don't go up or down at all to get here. I just go to the right 1. I do not go up or down. Sine of 3 pi over 2, -1.
Could you scroll back up?
I know, it was up there for a while. Okay, so let's just keep up with me, please. Why is the sine of 3 pi over 2 -1, Mr. Daves? Is that your name, Dave? What's your name? You're Miss Dave. You're Dalton. Why is the sine of 3 pi over 2 -1?
3 pi over 2 is 1.
Yep.
Well, you're going down. Well,
Yep.
It's going somewhere.
No. Distance
Going down.
from the
Okay,
origin. Because I go down 1 to get there. That's why the cosine of 3 pi over 2 is what? Everybody? Why? Because you don't go left or right at all. If you are struggling right now, we need to work together before Monday, because you're not going to be able to move forward in this class if you don't know this stuff. Let's just push on and finish when we finish. Moving on, we need to be able to reference our unit circle knowledge and our understanding of the triangles to solve trig equations. This is something that you have to know. So, how am I going to solve a trig equation? I'm going to first start by isolating the trig function. Solving by subtracting, by dividing, whatever you want to do to isolate the trig function. Now, I need to use my unit circle knowledge to figure out when is sine of an angle going to give me a value of 1/2. This is what I do. I first think, okay, sine, vertical. Vertical side length of 1/2. I'm thinking about creating a triangle with an angle where the vertical side length is 1/2. I know a triangle whose vertical side length is 1/2. It is a 30, 60, 90 triangle whose horizontal side length is √3/2. This is a pi/6 triangle, or a short 30, 60, 90 triangle. I need to find the pi/6 locations that give me sine values that equal a positive 1/2. You might think, oh, that's my answer, pi/6. That's not all my answers. We are looking for all solutions between 0 and 2 pi. 5 pi/6 is my other one. Now, here's an easy way to remember, like the other locations. I like to do this. Remember this acronym, ASTC, all students take calculus. This is telling me which trig function is positive in which quadrant. So, all trig functions are positive in the first quadrant. So sine's positive, that's why pi/6 works. Sine is positive in the second quadrant. So since sine of theta equals positive 1/2, that's why I know I need that pi/6 in the second quadrant. Now, what is it? Again, you have to be able to find the angle. I know this is 6 pi/6. Need to go clockwise. That is in a negative direction. So I'm subtracting a pi/6. That's why I know it's 5 pi/6. We didn't have to subtract 3 first, then divide by 2. You could have divided by 2 to start with. But what people don't understand is that if you're dividing by 2, you're dividing everything by 2. This is why we don't teach that. Yes. So this would be sine theta plus 3/2 equals 2. Sine theta equals 1/2. This, you don't have to distribute first. You guys are old enough to kind of figure out the different ways to solve equations. If I divided by 2, since it's 2 times this entire quantity, I could have just divided everything by 2, and the 2 would have gone away, just left me with cos theta minus 1 equals negative 1/2. And then add 1, I get cos theta equals positive 1/2. And now I need to solve. Cosine equaling 1/2. This is what I think about. My horizontal side length is 1/2. I'm thinking about an angle, and the horizontal length to that angle is 1/2. Okay, well, I know a triangle where the horizontal length is 1/2. It is my taller 30, 60, 90 triangle, where the vertical side length would be √3/2. This is my tall triangle, which is created from my 60-degree angles, which is my pi over 3s. So I need pi over 3 because I know that cosine is positive a half here. Where's my other pi over 3? In which quadrant? The fourth. Why? Because of either the C or it's like, oh, I need to know when it's going to the right. So the pi over 3 over here. How do I know what that pi over 3 is? I start with 6 pi over 3. I subtract a pi over 3, and I get to 5 pi over 3. If you are very uncomfortable doing this, you will need to practice. All right, let's do the next two. Ready, set, go.
The next one or the next section?
Next two. Yeah, that's a quadrant, sure, but like, you got the spot. What's the angle? Yep, pi, 180, yep. Now, reminder, we look for all solutions from 0 and 2 pi, including 0 and 2 pi. So the first one, we get x equals pi. For the second one, subtract 4 divided by 3. Well, after I subtract 4, I get the sine of x is equal to 0. Sine, vertical, vertical, 0, 0, pi, 2 pi. Okay. Now, all of our answers have been between 0 and 2 pi. We haven't had to look or worry about anything beyond that. But know that angles don't stop at 360 degrees. You guys ever watch the X Games? Ever seen cool kids on wakeboards? Okay? So if you're doing a 0, you're just going straight, right? You pop a 360, you're pretty cool. You end up in the same places where you were when you started, right? So 360 degrees, you started at 0 and you ended at 0, right? But it's different. Well, if you're really cool, you could pop a 720. Now, I'm really cool now. I just did 2 spins, but I ended up back where I was. But did I do something different than a 360? Yes. So we can continue to go around the circle and end up at the same locations, but they are different angles. Does that make sense? If you're able to pull a 4 pi, you're a lot cooler than if you could pull a 2 pi. All right? So we need to keep that in mind. If I took away this restriction and I said, find the solutions, you would have to consider all of the solutions where the angle that gets referenced ends up here at pi over 6 and here at 5 pi over 6. Which means if I go around the circle again and end up in the same location, that is a different angle, but it ends up in the same location as where pi over 6 is. Just how 0 and 2 pi end up in the same spot. Now, if I add 2 pi to pi over 6, what do I get? Well, let's think about that. 2 pi is the same as, okay, 12 pi over 6 plus pi over 6 gives me 13 pi over 6. That is technically a solution. If I start at 5 pi over 6 and add 12 pi over 6s, that gives me 17 pi over 6. And I can continue to go around the circle over and over again forever. There's certain notation that sometimes we use, like multiple notations, where it's like, take this at a multiple of 2 pi. Take this at a multiple of 2 pi. As long as you're adding an integer multiple of 2 pi, and you'll get all the solutions. We can also go negative. So this ends up being negative 7 pi over 6, and this is negative 11 pi over 6, okay? We didn't have to worry about that, though, because I told you 0 to 2 pi. Well, we will have to worry about that for these, which is why they're tougher. Because it's not just a sign of theta, it's a sign of a multiple or a divisor of our variable. And watch what we have to consider. Now, the first thing we have to know is that you can't get rid of the 2. So don't try to get rid of the 2. It's in the sign. You'd have to get rid of the sign first before you get rid of it. Instead, pretend like it's not there. Pretend it's just like the sign of something equals root 3 over 2. You can use a different variable like y if you want to. Let's just go with sign of something. Now, again, you got to use all of the stuff we talked about to be able to figure this out. Sine, vertical. What is my vertical? Root 3 over 2. Okay, my vertical, root 3 over 2, will happen if my horizontal is 1/2 and my hypotenuse is 1. So again, this is my tall 30, 60, 90 triangle that occurs at the pi over 3s. The pi over 3s, when sine is positive, are here in the first quadrant and here in the second quadrant. Pi over 3, 2 pi over 3. But these are not my answers. Because I'm not looking for just theta, I have 2 theta. This stuff inside 2 theta has to equal those angle measurements. If you wanted to do like a y, you'd say, okay, y has to equal that, but y is equal to 2 theta. Watch why that's important. Because to solve for theta, I need to divide by 2. I'm going to divide everything by 2. It's the same as multiplying by 1/2. So this turns into pi over 6. That is a solution for theta. This turns into pi over 3. Great. Those are my actual solutions. You take pi over 6, you plug it in here. It turns into pi over 3. The sine of pi over 3 is root 3 over 2, so we're good. But these are very much so inside of 0 to 2 pi. Remember, we want all of our solutions between 0 and 2 pi. What that means is that I might have to expand my first set of solutions that I found, that we just talked about, where I'm going to take these solutions and add 2 pi to them so that I get back to where we want it to be located, but it's a different angle. If I add 2 pi to pi over 3, well, let's think 2 pi is 6 pi over 3 plus a pi over 3, 7 pi over 3. Well, watch this. Take 7 pi over 3 divided by 2, 7 pi over 6. Is that between 0 and 2 pi? Yes. So that actually is a solution that we have to include. We want to get back to 2 pi over 3, but we want to go around the circle again. I'm going to add another 2 pi. Add a 6 pi over 3, I get to 8 pi over 3. Divided by 2, that's 4 pi over 3. This also between 0 and 2 pi. Maybe I need to do it again. Maybe I need to add 2 pi over 3 to 7 pi over 3. Let's see. 6 plus 7, 6 pi over 3 plus 7 pi over 3, 13 pi over 3. Let's see. 13 pi over 3 divided by 2 turns into 13 pi over 6. No. That is bigger than 2 pi. How do I know that's bigger than 2 pi? 13 divided by 6, bigger than 12 over 6. So I know 13 pi over 6 is bigger than 2 pi. So I actually understand the angles that I looked for originally so that my manipulated solutions are all the solutions between 0 and 2 pi. Let's think about this one. Cosine of x over 2 equals root 3 over 2. Ready, set, let's go. We could start by thinking about like the x over 2 not existing and just like thinking about what is cosine going to give us negative root 3 over 2. Okay, so go ahead, tell me and find out two solutions for when cosine gives me negative root 3 over 2. If this stuff is not mastered by Monday, you will struggle all year. Guaranteed. If you like how the beginning of a school year is a nice slow ramp up into material, not up in here. We hit the ground running. Cosine is negative root 3 over 2 at the pi over 6 here and here. Why? Because root 3 over 2 would be the longer side of my 30, 60, 90 triangle, which is created through my shorter 30, 60, 90 triangles at the pi over 6's, this being 5 pi over 6 and this being 7 pi over 6. You need to be able to get there. So there's that one and there's that one. But that's not my answer because it's the cosine of x over 2 that needs to give me root 3 over 2, negative root 3 over 2. What do I do to solve for x? Multiply by 2. Multiply everything by 2. 5 pi over 3 or 10 pi over 6. 7 pi over 3 or 14 pi over 6. Okay, am I done? Am I good?
No.
No? You can't have 7 pi over 3. This is bigger than 2 pi. Okay, so in the previous one, I had to expand. In this one, I actually needed to contract the angles that I looked at. But I can't figure that out until I kind of do the manipulations and I solve. Look at the next two. These sometimes confuse students. I'll show you a way you can do it so that it makes sense. Now, which triangle is the vertical side length and the horizontal side length the same? 45, 45, 90, the pi over 4 triangle, right? A lot of people will look at this and say, okay, sine is positive and cosine is positive at pi over 4. That's my answer, but they would be incorrect. And this is how I'm going to show you it. Let's not think about sine equaling cosine. Let's get rid of this cosine by dividing cosine by both sides. That gives me tangent equals 1. Tangent is not just going to be equal to 1 in the first quadrant. Tangent will be equal to 1 here in the first quadrant at the pi over 4, but tangent is also positive here in the third quadrant. So tangent will equal positive 1 at this pi over 4 as well. 0, this would be pi, that's 4 pi over 4. Add a pi over 4, I get to 5 pi over 4. Those are my two solutions. Some people see this, and they might think, okay, cosine has to be negative, sine's positive, but they're the same, and they go to this pi over 4 only. But they are wrong. A way I can show you that they are wrong is, again, if you divide by cosine, you have tangent equals negative 1. Tangent is not just negative here, tangent is also negative here, which is why I have two solutions at 3 pi over 4 and 7 pi over 4. Okay. Last one, then you guys are going to try it out. We will have lots of equations like this in this class. The key to this type of equation that I'm referring to is this. We will have lots of equations set equal to 0 in this class. And when you have an equation set equal to 0, having a product on one side will help us tremendously. Now, I do not have a product right now. I have a sum. I have this one plus this one. But we will be factoring very often in this class to turn a sum into a product. And I'm going to factor out a cosine from both of these terms. Now, remembering factoring is just like dividing, unless we're factoring like a trinomial, then it looks a little different. If I divide out cosine and theta from both of these terms, I'll have 2 cos theta left over from this term, because these cosines will cancel. And these will cancel, but it will leave us a 1. Now, the zero product property states that if one piece of a product is 0, the entire thing is 0. So that actually enables us to create 2 separate equations. This piece set equal to 0, and this piece set equal to 0. Go ahead and solve both of those. We factor, now we can solve. Check your answers with a neighbor. Okay, you factor a cosine out. Now you have this times this equals 0. Since it's a product set equal to 0, this piece set equal to 0, that set equal to 0. Two equations that you solve. So, cosine is the horizontal. Now, the answers to these equations are angles.
Okay.
So we're thinking like 0, pi over 2, pi over 4, pi over 3, stuff like that. Okay. Now, cosine horizontal. When on the unit circle, am I not moving to the left or the right at all, but I am moving up or down? In the middle, exactly. And what are those two angles in the middle? So, right in the middle to get here, which is 90 is pi over 2. Okay. Then I get to 180 now. I'm not in the middle anymore. I'm moving to the left. So here at pi, the cosine of pi is -1. Now I go down here to 3 pi over 2. Am I moving to the left or to the right at all when I go down? No. So that's your other one. Cosine equaling -1/2. Thinking of a triangle where the horizontal side is the half. Okay, that's when the vertical side is √3 over 2. That's my taller. That's at my pi over 3s. But cosine is negative in the second and the third quadrants. So I need the pi over 3 here, and I need the pi over 3 there. You can start with 3 pi over 3, subtracting a pi over 3 puts you there, adding a pi over 3 puts you there. So 2 pi over 3, 4 pi over 3. Those 4 angles will be solutions for this equation, which is pretty cool. You can list them off in order for practice. Let's solve these last 4. What happened? What did I do?
Sine is negative. It's supposed to be sine is negative, sine is positive at 3 pi over 4.
Whoa!
It should be 5 pi over 4, not pi over 4.
My bad. Thank you, Ms. Davis. Look at that. Lot of solutions by adding 2 pi. Okay, I had to continue to add 2 pi because whenever I took this and divided it by 3, my angle got significantly smaller. So I actually had to add 2 pi twice, which is pretty cool. And this guy, when it's sine 0, so that's when I'm not going up or down at all. 0, pi, 2 pi. When do I go down 1 unit? 3 pi over 2. Okay, you isolate the trig function. You then think of the triangle. You think of the location of the triangle. For cosine x equals negative root 3 over 2, cosine being the horizontal, I need a triangle whose horizontal side length is root 3 over 2. That's the shorter 30, 60, 90 triangle. Those occur at the pi over 6's, the 30 degrees. I need the pi over 6 when cosine is negative, though. So I need this pi over 6 and this pi over 6. 6 pi over 6 minus a pi over 6 plus a pi over 6 gets you that. Next one. Oops. The next one, we end up just thinking about cosine equaling a half. Half for the cosine, the adjacent side, the horizontal side, so it's the taller. When is cosine giving you positive? Here and here. This taller is at a pi over 3. So I need the pi over 3 in the first and the fourth. That's pi over 3 and 5 pi over 3. Why is it 5 pi over 3? I go to 6 pi over 3, subtract the pi over 3. But then, to solve for x, I multiply everything by 4. When I multiply this by 4, it's 4 pi over 3. That's good. I multiply this by 4, it's 20 pi over 3. That is not between 0 and 2 pi, so that's not good. Here, when it's, I was thinking of cosine again. Sine is negative in the third and the fourth quadrants. It's equal to root 2 over 2 at the 45 degree angle, so that's the pi over 4s. So that's why we have starting with 5 pi over 4 here, and then 7 pi over 4 here. But when I solve for x, I had to multiply things by 3. Sorry, divide things by 3, giving me 5 pi over 4 turned into 5 pi over 12. Definitely between 0 and 2 pi. I need to get to 24 pi over 12. So that's why I continued to add 2 pi to get to the same angle location, but different angles, and continue to go until I get to something very close to 2 pi, ensuring that my next one that I found would be beyond 2 pi. Finally, this one, again, we factor. We have an equation set equal to 0. We have 2 equations after we factor that we solve. One is sine 0, at the horizontals when assigned -1 at the vertical on the bottom. If you cannot do this quickly by Monday, you will struggle for the rest of the year, guaranteed. Because we move on, and trigonometry pops up occasionally. And if you don't know what you're doing, every single trig problem is going to really weigh you down and hurt you for the rest of the year. So your plan is, if you struggled, you're going to come in and see me. And we're going to make sure you're struggling less by the time we take the quiz on Monday. This is not, oh, I'll be fine. It's still the first couple days of school. This is, you must know this right now, or you are going to not like this class. All right.